Afternoon, everyone. I slipped up a bit on Friday because I said that Rob Waite was going to be this afternoon, but he's been panicking a little bit. Don't know whether he's got his acro presentation ready or not, but it's not actually Rob Waite. We're back on schedule now, so it's actually Russell Lane from HK. Doing some product training or introduction for the Metal X. So, are you about, Russell? Can't see.
Yeah, I'm here.
Okay, I'll mute myself and hand over to you. All right.
Thank you, sir.
Good luck. Catch you later.
Thank you. Right. Let's wait for that to kick off. All right. Good afternoon, one and all. Thank you for your time this afternoon. As Mark said, I'm Russell Lane. I'm a RSM for HK, and today I'm going to talk to you about the Markforged Metal X. A few little bits of housekeeping. So if we could make sure our microphones are on mute so I can avoid any heckling or that I hear until the end of the presentation. We will open up for Q&A at the end, both through the chat feature in Zoom and both audio questions as well. I think Martin is looking to record this as well, so I think record button's already on. Happy days. So today what I'm going to talk to you about is ETG and HK, where we fit within the HK group. What is 3D printing? Hopefully not too much of a shock to anyone. The Markforged Metal X and the ecosystem that comes with. The materials that it's able to be printed in, applications, and a bit of return on investments, followed by some Q&A. So within the ETG group, obviously we're a privately owned organisation. We specialise in CNC solutions, EDM, turning and finishing, as well as 3D printing now, or additive manufacturing. 123 employees over 3 sites for the UK and I, specialising in aerospace, defence, automotive, energy, to mention a few. As some of you may be aware, this additive manufacturing is made up of 7 different technology sets. Within our partnerships from Markforged and 3D Systems, we have exposure to 5 of those 7. But today, what I'm going to talk to you about is material extrusion, or FDM, FFF, or just to chuck another acronym in there, ADAM, which is Markforged's FFS solution. So FFF stands for Fused Filament Fabrication or Fused Deposition Modeling, and ADAM as a Markforged acronym stands for Atomic Deposition Additive Manufacturing. It's the most common form of 3D printing. It basically consists of a build plate, which is the part in the picture at the moment with a triangle on it, an extruder that will be flying around in a second, and the filament that is squeezed through that extruder. So as you'll be able to see from this video, the bed is slightly lowering, the print head where the extruder is stationary, creating a part that's left behind. Within metal, you'll see, or within the Markforged metal process, you'll see a white line being created. That's a ceramic layer, which when it's been sintered, enables things to be broken off quite quickly. So this is the Markforged suite of products. We have the composites over on the left-hand side, which is the desktop, and the industrial, which my colleague Lee spoke about in a week. And on the right-hand side, we have the Metal X printer, the Wash one, and the Sinter one. We also have a Sinter 2, and I'll show you some images of that later on. In addition to the solution that you see here, the things that a customer will need will be things like an extraction system for the Sinter, just to take away any potential harmful gases that may be in the atmosphere. Some Optium Scion, which is the wash liquid. That's an evaporative process, but I won't go into that in too much depth, but that basically gets one part of the binding solution out, and some gases to enable us the inert chamber within the Sinter to take that from a waxy plastic powdery format into a solid part. What Markforged have done really well is take metal additive manufacturing from the exclusive ends of customers and businesses that wanted to spend £1 million plus on a metal solution, to businesses that are able to spend £150,000, sorry, on a metal solution and still give you a huge amount of materials and some other benefits that I'll talk to you through in this presentation. So what Markforged, or Greg Marks, who was the CEO of Markforged, created when he came out of MIT, was he wanted to look at his customer base and deliver them some features out of products they were printing that they hadn't had before, such as good quality parts, low failure rates of the printer, high print success rate, and equally so an intuitive software solution that was not just aimed at the pinnacle of additive manufacturing engineers. So what we see here, we have in the top left-hand corner, we have Eiger, which is the Markforged slicing software. So taking a CAD design, putting it into Eiger, and then Eiger will do all the heavy lifting in regards to slicing, sizing, ready for printing. Greg also looked at it as a bit of a database, basically, and looking at, actually, if I put poor material in or poor information in the front end of my database, regardless of what happens at that processing of the database, the back end, I'm still going to get a poor output. So what Greg did, he created his own, or Markforged created their own material, both on the composite sides and on the metal sides, to enable the printer to make sure that it's printing successfully. And then we're talking 96, 97, 98% of the time. And so from an end user point of view, what that means is you haven't wasted and invested a lot of time and effort on a print, which is a waste of time and effort, and then you have to redo it again or look at another solution to achieve that. So in a real nutshell, in regards to the key features of that particular range, what it has done is it's a low entry point to additive manufacturing. If you compare that to the likes of the DMLS, so direct metal laser sintering, which is a powder bed environment, which we're also able to sell through our colleagues at 3D Systems. It's a very low failure rates of the products, a high success rate and capabilities and consistency of print. So when I say consistencies, I'm talking about sizes that come out of the back end of the printer. So there's not a great deal of fluctuation, resulting in a lot of post-processing when that's finished. There's no need for a hazmat suit, no need for really expensive purpose-built facilities. So if we look at, you've spent £1 million on a powder bed environment, then you have to spend potentially another £1 million getting a facility to hold all that in one place. It's not needed for the Metal X solution, so it's very easily installed into an organization. As I mentioned earlier, you will need an extraction system, and that's just purely for the sinter. There's no need for a highly skilled operative to watch the printer when it's run. Eiger, as a slicing software, will email you when the print is done, so you can almost print and forget until you get an email, effectively. And material swapping to go from one material to another takes about 15 minutes. In a powder bed environment, you're probably looking at 3, 4, 5 days to get that printer sorted to enable it to be printed in another material. Effectively, what customers will then do is go and buy another printer. So they now have to spend £1 million plus another £1 million for a facility. So you can see where the scales of economy wrap up to look at a Metal X over the competition. With the variety of materials we're able to present, obviously you can see them on the left-hand side in blue, but effectively what we see here is stainless steel, tool steels, Inconel copper, and a few that are in development. Stainless steel is one of those materials that, it's been around for a long time, but it's almost, from an additive manufacturing point of view, a replacement to that of aluminium. So when we're sort of going to customers, and customers says, actually, we mill all of our parts out of a billet of aluminium, we can think, actually, this brake lever here, which was originally aluminium, weighed about 180 grams, and now printed in stainless steel, and I'll show you some more details of this later on, but now printed in stainless steel, so a more dense metal, a stronger metal, it's now half the weight, but gives you a better strength profile than the original part in aluminium. With regards to H13, this is a really good for high temperature environments and high wear, so we're looking at the likes of gears and where it's been two metals being pushed together. From a D2 point of view, it's a hard, from an A2 point of view, so a hard material, but good for impact, so the likes of dies and cutting, dies and punches, and as well as hammers, for example. And then D2 is somewhere where you can print your own cutting tools. Obviously, you need to sharpen those post-process, but it will give you that material ready to create those cutting tools as well. Inconel and copper share although very, very similar, very distant metals apart from each other, but Inconel and copper share a similar property in the fact that they hate being worked, hate being post-processed, and the more you do, the harder they get to work and post-process, creating defects within the material, lending themselves ideally to additive manufacturing. So we can print them in their net near shape, and the only thing you need to do then is just a little bit of shaping to make sure you get the surface finish right or the dimensional accuracies that you need. Inconel, obviously, very, very good for very high temperatures, whether it's exhaust manifolds for cars and Formula One, all the way through to aerospace. And copper, obviously, it's highly conductive for electricity. So the likes of Tesla are using that quite effectively currently, but equally so can be used for spot welding and other applications that include that use electricity. And another thing about the copper over its peers in the marketplace is the Markforged copper is pure copper, rather than having elements in there to enable it to be melted together, because obviously it's a very soft material. And obviously from a 316L and titanium, their metals are going to be released very, very soon as well. From an application point of view, what we have here is an end part from Schalke orthopedic surgeons. And this helicopter socket, as it's lovingly called, is a part that used to be CNC'd out of medical grade material that cost a huge amount of money to produce. There was a huge lead time associated to that as well. And what Schalke do now is they print it out of stainless steel, enabling them to reduce that cost of entry from $1,400 down to $120. And this is for functional prototypes, so to allow those orthopedic surgeons to practice on different types of braces and products that are being put onto patients' skulls and bones to hold them in place. And then as a result of that, there's some huge savings both on a cost and a lead time perspective, giving that some real good value back to Schalke and the end users there. From custom tooling, so this is a part of the Markforged in the US have been working with the military for quite some time now to reduce the amount of weight carried in their Bergens. So an engineer in field will carry a toolbox that could be anything between 10 to 15 to 20, 25 kilos, in addition to everything they're supposed to be carrying on a day-to-day basis. By changing their spanner setup from a solid lump of metal with multiple heads, we've now changed it from a composite shaft with embedded carbon fiber or Kevlar, depending on what it's being used for, and an interchangeable head printed on the Metal X, which they're all doing in situ, in fields, whether that's at Camp Bastion or other places as well. So you show some good hybrid features of where the Metal X composite and Metal X work together very well as well. End-arm tooling. So this is lean machine in the US, and this is, one thing that we're asked is CNCing going to be replaced by additive manufacturing? And from my point of view and from the rest of the team, absolutely not. This is where the additive manufacturing side are working hand in hand with CNC to make CNC even more beneficial to the customer and more profitable. So the low value, low volume work is being taken away by the robotic arms and those pincers that there are printed in on the Metal X. And then now they're taking away the labor intensive bending of little steel bars to enable them to go on to another process, freeing up some bandwidth on the CNC machine to do the more profitable work. And here's my brake levers that I lovingly showed you earlier. So in the top right-hand corner, what you'll see is the same brake lever, but printed on the far right-hand side and then sintered on the left-hand side. And what that means is that when we print something, your STL will be of a certain size, whether that's say 10 centimeters or 10 millimeters long. Oh, sorry, let's go with 10 centimeters. And then what Eiger will do, Eiger will increase that by a factor of 17 or 20%, depending on the thickness and the orientation, to enable it to be shrunk as it goes through the sintering process. And again, lightweighting, as we talked about earlier, a part that used to weigh 180 grams is now 99 grams, and now using a stronger profile of metal and steel as well. Just to reiterate what I said earlier in regards to the, where's my last one? So when you design your part, so this is your CAD design, when it goes through to its print, it will look a lot larger and it will be a lot larger until it gets through to its sintered process. And once it's goes through its sintered process, you'll be left with your end part back to your normal size that you've set up. And what I'll do now, I'll just introduce you to one of my colleagues in the US called Trip Bird, who's a senior applications engineer, just to run through that in a little bit more detail. 1 second. And I do hope I haven't closed him down. Here we go. Great.
At this stage, your part is full.
There we go.
Hey, everyone. everyone. I'm here to talk today about the Markforged Metal X process. It's a simple, safe, and cost-effective method to go from design to functional metal part. There are 3 steps in this process: printing, washing, and then sintering. First, let's start with CAD. You design your part, then export to STL and upload into Eiger. Eiger is a cloud-based slicing and print management system that comes with every Markforged product. This automatically configures your part based on the material and printer you've selected. When your part slices for metal 3D printing, it gets scaled up to account for shrink and deformation in the downstream processes. It then slices your part into discrete layers, identifies overhang features, and builds supports and a raft underneath your part. As we go through printing, washing, and sintering, Eiger will monitor the part's progress along the way. Let's start this print and go to the Metal X. Before starting a print, the machine automatically maps and levels the bed to ensure the first layer goes down well. Your print is built of 2 materials stored in this heated chamber above, one of ceramic release material and one of the metal to be printed. This filament material is metal powder safely suspended within a 2-part plastic binder. It gets heated and extruded onto the build plate where the part is created layer by layer. The release material gets extruded as an interface between the part and its supports, so that once your part comes out of the furnace, it's easy to remove. Unlike other metal 3D printing systems, this process does not require loose metal powder, resulting in a safer and more cost-efficient workflow. 17.4 stainless steel is loaded now. However, with a quick changeover, the system is capable of printing in stainless steels, tool steels, coppers, Inconel, along with several other materials currently in development. Once your part is finished printing, you'll get a notification. At this point, you can go to the printer, remove the part from the build tray, and clear the bed. Now we have what's called a green part. It doesn't really look or feel like metal. However, a large part of it is comprised of metal powder. Next step will be putting it into wash 1 for the debind process. Wash 1 removes the first stage of the binding material. A green part is taken from the printer and placed into the wash basket, which is then lowered into the solvent. Wash times will vary, ranging from a few hours to a few days, depending on the thickest region of your part. After that, it's now called the brown part and is ready for sintering. Let's go over to the furnaces. This is Sinter 2, a furnace designed for mid-volume production runs and larger printed parts. Sintering transforms a print from a lightly bound collection of metal powder to a fully finished metal part. First, the temperature ramps slowly to burn away the trace amounts of remaining binding material. Then, temperature ramps closer to the melting point of the material, allowing metal particles to start to fuse together to create a strong metal part. Markforged sintering furnaces use a carbon-free retort to ensure part quality and alloy composition standards are met for our finished pieces. Each run takes about a day and can be monitored remotely using the Eiger software. Once a run is complete, the center tray full of finished metal pieces can be removed from the furnace. Once removed from the raft, these parts are ready for use. In the furnace, the layer of printed release material between supports and the raft and your printed part remains powderized. This allows the structure to be tacked to the raft to better control shrink and accuracy throughout the process, but also an easy release after sintering.
There you go. I'll cut Trip off in his prime so I can get back to this. There we go. Okay. So the part that Trip was going through in that video was a part for one of Markforged's customers in the UK called Stanley Black & Decker, pretty much a household name. But this power driver, or the post driver, had a critical fault in it, in the fact that the part at the top on the right-hand side that is circled in orange square kept on failing. So what they came to Markforged and asked, as do many of our customers, saying, actually, can you print this part for us? And most of the parts that we get given haven't been optimized for additive manufacturing. So what Trip and the team did is they designed or did some design for additive manufacturing. So they took if you look at the blue part on the top, so as you can see, it's made up of 4 different parts. So a cast part at the back in blue, a blanking plate and 2 bolts. And the seal kept on failing between the blanking plate and the mold. And there's circular holes in there, and obviously because there's a 90-degree bend in there, it wasn't able to be manufactured by any other format at the time other than being molded. So what Trip did, so the part at the bottom is the end piece that he was placing into situ. Rather than having circular holes, they've now teardropped those or put a square on its side. So basically all the infrastructure self-supports itself, so there's no need for internal supports on that part. after testing and rigorous testing by the team in Black & Decker, they found that the cost reduction had been in excess of 40%. Lead times were nearly 70% faster. There was a cost reduction of in excess of 90%, and lead times were 95% faster as well. So showing a real true return on investment back to Black & Decker, and this is now a mass-produced part for their post drivers within the company as well. So as some key takeaways on the Metal X, just like to reiterate, this is the most cost-effective and easily installed additive manufacturing solution in the industry. It has high levels of repeatability, consistency. It's an industrial additive manufacturing solution designed for prolonged periods of uptime. Working at a 24/7 is what it's built to do, rather than just short runs. There's a wide variety of materials. There's an ease of swapping out of those materials and in minutes rather than days. It's covered along with all the other Markforged product in a full accidental damage success plan, giving peace of mind back to our customers that their printer will be down for a very, very short time if it goes down at all. There's no need for a highly skilled, highly paid operative to oversee that printing, as it's all done, and it will be pretty much a print and forget machine until such time as it's finished printing, and you'll receive an email telling you that it's ready to go into the wash or into the sinter, or take out the sinter and be used. And there's no need for any hazmat suits, breathing apparatus, or highly expensive additional dedicated facilities to in-house our machine. So if you have any questions, I'd love to take them on board. Thanks for your time.
Thanks for that, Russ. That was a cracker.
Thank you, mate.
So, as usual, the chat bit is open. So, anyone want to pipe up with any questions? They're getting skilled at it now, Russ. So. No questions. Oh, Steve Brown's got one. Yep. Go over to you, Steve.
Hi there, mate. You all right? Can you hear me? Yeah, I'm off now. Right, great presentation. So your opening comment was regarding the cost of the unit versus, like, I don't know whether the alternatives. And I've heard that comment before, not just through the Markforged side. So have we benefited much from that? Is there much more competition? Is there many other people able to print metal?
Yeah, so there's been quite there's another company basically called Desktop Metal. There's been some good legal conversations going on between Markforged and Desktop Metals over the last few years, of which, glad to say, Markforged have always come out on top, to the point that the legal fees are all going back to Desktop Metals for random allegations and failures to print. But yeah, there's probably the two, either Markforged or Desktop Metal are in a similar sort of price band. There's definite benefits over Markforged and there are Desktop Metals in regards to making sure that there's a successful print at the end rather than a failed print. But yeah, they're probably the two that don't use a DMLS or powder bed environment that are the closest to each other.
And when you go from one material to another, is there like a cleaning process that you have to go through? Do you have to wait hours to go from one?
No, literally, I could finish. This is a brake lever that was printed in stainless steel. As soon as this is finished printing, we can. So you let the bed cool down for a little bit, and then you open up the doors at the top. You take out in this case, stainless steel, and then replace that with whatever metal you wanted to. There's as with everything, the filament is quite brittle when it's in its cold format. That's why the heating chamber's at the top. So when the bed heats up, that heats the filament as well, and then it's ready to print. So yeah, we're talking 15 minutes from end print to your next print and in a different material.
Right, okay. So I'm going to ask a really stupid question. Does it only do metal?
Yes.
Yeah.
Well, yes. Well, metal and a ceramic layer. So yeah, only metal.
Yeah.
So that's why we have the composite range doing.
I'm trying to stop laughing, but I knew it was a stupid question. But I have to ask.
Oh, I'm happy with that level of question.
Yeah, you don't get any more technical than that from me.
Perfect.
Well done, mate. Thank you.
Thank you.
What's the name of it again, Russ? It's called a Metal X, isn't it?
Correct.
All
yeah.
right, Martin. Next question.
Mike Jardine.
Hi Ross, good presentation.
Thanks, sir.
So, quick question. There's a few references to hazmat suits. And the question is, does that indicate that a lot of the competition or alternative machines require this?
Yeah, absolutely. So if you're working in a powder bed environment, so the differences are that the powder bed are and they're great printers. Don't get me wrong. If you're spending £1 million or $1 million on a printer, they're going to be really good. But the powder that they're using is smaller than your skin follicles. So if you get any on your body, basically it could be the next asbestosis. Effectively, that's why from a Markforged point of view, there's no real health and safety sort of concerns apart from the sintering process where there needs to be an extraction fan. But in regards to the actual material, it's housed between a wax polymer and a plastic bonding agent that keeps it in its filament rather than being loosened in the air. So yeah, if you've got a DMLS process, which is the powder bed environment, you will need to have some hazmat facility or a dedicated facility to house that machine in.
Sounds quite an operation.
Yeah, and it's an expensive operation as well. Yeah,
I can imagine. Thank you.
Gareth Jones.
A good presentation, Russell. You spoke very well. So just picking up on the applications that you spoke about, which were all about Markforged research and their development and what the successes that they've had with the technology. Can you tell us some of the successes or the projects and applications that you're working on relevant to the UK market?
Yeah, so within the UK, there's a huge demand for universities to sort of adopt this technology. You know, that over the years they've invested huge amounts, and we're talking millions in powder bed environments. And now that the Markforged is, you know, as Markforged are globally the biggest sintering manufacturer in the world, they've now taken a real good stance in developing proper additive manufacturing and metal additive manufacturing solutions that are going to be needed by the next level of engineers coming out of university. So within university, there's a huge amount. Within aerospace, there's also a requirement for non-flight. So obviously, not many processes have been approved for flight for additive manufacturing. Not saying it won't be, but there's a lengthy process to go through that, and it's not just the process of certifying a billet of titanium and then milling that down or printing that. Then you need to take into consideration the orientation of a part, and that will always change. But yeah, so where it's non-flight critical, so on land, we're working with some well-known airlines based around Luton and in Ireland to work with starter motors for their planes. So basically printing out the full fan construction for a starter motor, giving them, and the whole fan rotor will cost about £400 to print, where it will be about £16,000 to buy from the manufacturer. And equally so, the MOD and military within the UK, to mention a few, are very, very keen on looking at this solution and trying to push that as far forward into deployment, not necessarily just in the UK.
Thank you.
Jamie Fletchmore, you've written your one out. Do you want me to read it out for you, or are you happy to ask the question?
You can ask the question, yeah, no problem. Well done, Russ. Just a quick one there. For electrodes for EDM machines, is it possible to print the electrodes out of copper? And also, how accurate would this be? Because sometimes when people are machining electrodes, it can be very complicated and long process time. So would this be an opportunity for that?
Yeah, well, it's definitely something we can look at. So what the Markforged will say is that over a course of a couple of inches, it will be either plus or minus about 120 micron accuracy on the actual print. But because there's a really high level of consistency, and let's say you print it in the middle of the print bed and it's 100 microns too big, then obviously that's great, because then you can obviously sand that back to or machine that back to the right accuracy. If it's and equally so, if it's 100 microns too small, you could then increase your STL or your CAD file by 100 microns to give you that dimension accuracy. But it's definitely something we could look at as a test within copper. Absolutely.
Yeah, just to come in there, Jamie, we've already started to embark on testing that application. As soon as the synth is set up in the showroom, Sarah's been working with Scott Ellesmere to actually print some initial electrodes to see how we get on with using them in the application.
Okay, that's great. Thank you.
Pleasure.
Jen has got a question. She's typed it out. Would you? But it's only to me privately. Are you happy to ask the question? Unmute yourself, Jen, or do you want me to ask? I'll unmute you. Hang fire. Go for it.
Yeah, I mean, with my non-technical hat on, I only, you know, it's not been very long that I've been introduced to the company and the products and everything. Obviously, with what's going on in the media at the moment, are those 3D printing machines the type of machines, the technology that make the components for sort of things like the face shields and that kind of equipment that's very much needed at the moment?
Absolutely, a great question. So yes, not necessarily the Metal X, but definitely the composite printers, and equally so the 3D systems part of the business. Absolutely, they're the types of printers that can do that, and they'll be able to do it a lot quicker than the Metal X. So, but yes, they're the same or similar types of printer that will be able to achieve that. Yes.
Thank you.
I think, Sarah, you've got something running out there now. It's not on the Metal X, but you've got something running for medical parts, haven't you, at the moment? Can I unmute you? You having your ponytail done?
Yes, apparently so. Well, yeah, no peace when you work from home, is there? Yeah, we're doing some parts on the composite machines, and their fixtures are going to a company who are making ventilators. So yeah, we have had them running for the last 3 weeks or so. So yeah, we've been doing a bit.
Good. I'll mute you. Get it back to your hairstyle. Steve Brown.
On the Metal X, what is the capacity size? You know, I'm just thinking that we do get requests for machining one-offs or two-offs or so forth. But again, if it's worth looking at printing a said part, but what's the sort of like the volume of the part that you could print? Yeah.
So effectively, the bed size within, and that's the platform that you can print on within the Metal X, is 250mm by 183 by 150mm high. But the sinter itself is you can call it the bottleneck. So the sinter one that we've got at the moment has a build volume of about a piece about the size of your fist. So if you can imagine it, anything around a 10 centimeter squared part would fit into the sinter one. The sinter 2 will take a significantly larger part. So you saw in the video from Markforged, that can take about a 15 centimeter high part. But again, depending on what the part is, we may want to look at orientation. And yes, so effectively, and what the wash time for a dense part, it was just a solid piece of aluminium, a solid piece of stainless steel the size of my fist, that would take a lot longer than if we'd have shaped it or done some design for additive to improve the flow of the oxygen side to increase the wash speed as well.
Yeah. Okay. All right. Cheers, mate.
Thank you.
Gareth, you have another question?
Yeah, so just putting you on the spot a sec, Russell, really. So what do you consider, in your opinion, to the key benefits of ETG as a group having this technology? What do you think are the synergy benefits there?
Well, I think the whole additive manufacturing benefit to ETG Group is the fact that we've got a huge amount of customer bases that are already using us as an organisation, so the ETG Group, and a large percentage of those will have already dipped their toe in, whether it's done research rather than going out and actually speaking to manufacturers or suppliers to embed additive manufacturing within their process. It may not be for their end part, but like we had with Lean Machine in the US, it's not about replacing their CNC machine or their milling machine. It's about improving the efficiencies and profitability of their organization. So if they can offload the more cost, the low volume, maybe parts that can be offloaded into another process through additive manufacturing, and leaving the high profitable parts to be printed, to be milled on the CNC or whatever their other technologies are in-house, then that's a real value to our end customers, and equally so increasing our stickiness to our customer base as well.
Great, thank you.
I've got a question for you, Russ. You mentioned earlier about the certification side of it. specifically in the aerospace industry?
Yep.
Because we know that it's been going on for years, hasn't it? You know, we've been trying to get into the hot parts of the engine and stuff with this technology. What is it that's stopping it getting certified? Is it the quality of the components that are coming out? Is it purely just time? Is it what's the problem?
It's a cost, actually. So some of the partners I'm working with that are working and certified part 21, so which is basically a spare part for an aircraft, or a replacement part that's now gone obsolete and they're just using it for servicing. It still has to go through an IASA certification. So as soon as it goes anywhere onto airside or to do with an aviation, it needs to be certified. So these rotors that I was talking about for the Orange Shed in Luton need to go through, even though they're not airside, they're still going to, or they're airside, but they're not going to be touching the plane, they're not going to be leaving the floor. They're classed as airside. They need to go through a lengthy process. And because additive manufacturing hasn't been, shall we say, adopted widely by aviation on a civil front, military are a different sort of kettle of fish because they're able to pretty much self-certify themselves. But as soon as we're talking civil aviation, the amount of hoops you have to jump through at a huge amount of cost becomes quite prohibitive to a supplier to an aviation company. So yeah, that's normally the sticking block of saying, actually, to get this brake lever certified for a starter motor or a cockpit, all of a sudden, then this may only cost £500 to print. The original may cost £5,000, but the certification may be £10,000 for that supplier to go through that whole process and take 6 to 8 weeks to actually do as well.
Thank you.
Thank you.
I think that's all your questions. I'm going to unmute all at the same time so we can give you a clap. Thanks very much, Ross. Cheers. Well done.
Thank you. Now the heckling starts.
Yeah, that was a great one. Thank you very much for that. So tomorrow we're back on schedule now then. So tomorrow we've got, oh, for God's sake, Graham Thomas. I don't know whether I've got enough disk space for the recording.
I'll try and break your recording tomorrow, but I've got a lot to live up to looking at some of the presentations so far, so it's going to be interesting.
I don't think I've got enough memory on my computer to save the thing, so we'll just, yeah.
Yeah, I thought you'd say that. Thank you very much.
Should we start at lunch?
So
can we go over to the free platform that's only 40 minutes?
So tomorrow, Graham Thomas is going to enlighten us about the Chiron DZ range of machines. So same time, same place tomorrow. Have a good evening. I'll see you later.
See ya.
Yeah.
Cheers. Cheers.
Bye, guys. All the best. Thanks so much. See you. Bye-bye.